So this session doesn't have a chair. I'm going to introduce myself briefly. I'm Reut Tsarfaty, now at Bar-Ilan University and AI2. I had a NLP lab. We're leading research, interdisciplinary research in several different areas. The lab has an interdisciplinary team of computer scientists, linguists, data scientists, software engineers, and we investigate various projects. Mainly 3 topics. One is natural language programming. This is turning language into something executable. I'm not going to talk about it today. One is about deep semantic parsing, using deep models to extract deeper semantics from text. I'm not going to talk about this either. And the third, but actually first in the chronological order, is our project on building infrastructure for Hebrew natural language processing, and I'm going to talk about it today. So let's start with the essence of natural language processing. And really from a bird's eye view, what we want to do in natural language processing in NLP is to turn unstructured texts into structured insights. And these insights can be formed in terms of tables or a certain database you want to populate with useful information for our business, for our application. Or it can be some agent like Alexa that executes the commands or the requests that we pose in our own natural language. So this little blue arrow that seems to be doing a lot of things, it seems to be quite a useful thing to have. But if you want to look a little bit into this arrow, then what happens inside is actually quite a bit more complicated. This is an example from a very famous natural language processing pipeline by Stanford, Core NLP. Maybe some of you have used it. And it shows different levels of processing for natural language. So the first level, which is quite superficial, is assigning each of the words its own part of speech tag, if it's a noun, if it's a verb, an adjective, and so on. It can recognize entities like Tel Aviv or New York or a name of a person, name of a location, organization. And it can identify the dependency structure, these bilexical arcs that represent essentially who did what to whom, without going into too much to the details. Here's a more complex example, maybe timely. The president of China on his first visit to the US, show his familiarity and so on. So we have a named entity recognizer that identifies the person, the location, China or United States, the timestamp, Tuesday night, and so on. Sorry. We have a coreference element that looks at the item his and knows to connect it to the president of China. And we have a very complex dependency structure that essentially is the basis for extracting further information, extracting the deeper meanings. So many applications, many successful applications actually assume this sort of NLP pipeline at their backbone. And there are successful pipelines. There's Stanford Core NLP that I just showed you. There is Spacey. This is very easy to install. This is very fast and very accurate. And there's also UDPipe. This is the third item that maybe you're not familiar with. And what UDPipe tries to do is to execute it for, actually train and execute NLP pipelines for over 80 languages. That's quite a lot. Let's see what happens when we take UDPipe and we try to parse a sentence in Hebrew. So I took Ganan Gidel Dagan Bagan. Hebrew-speaking people in the audience know to parse this sentence quite successfully, quite easily. If we take UDPipe and we give the sentence to the parser, we get, I'm going to translate it for you since I do not assume that you're all linguists at the audience. The first 2 lines tell us that Ganan Gidel is a proper name. Proper name like Reut Tsarfaty, okay, a person, Ganan Gidel. The gan is the verb, according to UDPipe, to fish, right? He fished them, something like that. And Bagan is actually written here as a construct state now. This is also not entirely correct. So essentially, almost none of the elements of analysis that you get from UDPipe is correct. And it's worth telling that this is the neural network models that we know and love, and they're trained on annotated gold data, and they use the most advanced method we're familiar with in NLP. These methods work for many languages, but for English, for this very simple 4 letters sentence, it doesn't work very well, and you can try it. Actually, it has an online demo. You can try it with whatever sentence you like and see. It's quite disappointing. So the question is, what's going on there? how come these models that are very successful for other languages really fail on Hebrew? And what I'm going to do in the 20 remaining minutes is to try to get you a little bit into this black box, show you why these NLP pipelines for Hebrew and similar languages actually break, and how we can fix it. Okay, so this is key problem with Hebrew, that Hebrew words cannot be trusted. So don't trust them. If you get a word like this one, so Hebrew-speaking people, what's written here? Okay. Maybe the coffee. This is if you're, very tired. It can also be an orbit, right? If you're talking about the Bereshit spaceship, or it could be the coffee. And interestingly, if it's the coffee, it corresponds to two different words in English, right? The coffee. So there's essential assumption about English that every word corresponds to basically one unit of meaning that breaks down. A word in Hebrew can correspond to multiple units of meanings, which for simplicity I will call morphemes. And it gets more complicated if we get a word like this. What's written here? Okay, maybe it's political, but maybe I'm talking about betzalam, habatzal shelam, their onion in the picture. Maybe I'm talking about the tzel, the shadow, in the pleasant shadow, betzilam, right? The shadow is also in the picture. Or I can talk about the tzel and protesting somewhere, that's also in the picture. So there's extreme ambiguity, and I didn't even list all the possible analysis. And how do we know which one to choose? We only know it if we have context. So if we have something about Irgun B'Tselem, we know we don't have to split the word to decompose it. And if I'm talking about me sitting in the pleasant shadow of something, then I know that I have to decompose it. So one, I need to know the decomposition in order to know the interpretation. But in order to know the interpretation, I need to know the decomposition. We have this loop where the meaning needs the decomposition of words, but the decomposition of words needs the global context, the global meaning. And we have to somehow break down out of this loop, and breaking out of this loop is the key challenge of Hebrew NLP. Okay, so what did people do? We're of course not the first ones to observe that. And I would say there are three main approaches to deal with this difficulty. One is the approach that I call the null approach. And this approach simply says, pretend that Hebrew is like English. Just don't do anything. And this is actually more common than you might think. Every time you hear that we have a new word-to-vec, pre-trained model upload to someone's website, or a multilingual BERT applied to Hebrew, these all assume that Hebrew is like English. So they ignore the word internal complexity and word internal ambiguity and use the English-based method. Is it okay? It can be, but it's not the best, most ideal strategy to deal with Hebrew. For some tasks, it will just give us results that are lower than what we expected, and for other tasks, it will simply be impossible. Where would it be impossible to use? For instance, if I have this sentence, ישבתי בצל העצים, if I do not break it down, I cannot assign a dependency structure to this sentence or a logical formula to capture the meaning. So while this is an okay methodology, it is not viable. It will not give us the accuracy that we want. It will not allow us to develop more tasks. So the second approach down the line is let's make Hebrew look like English. Let's apply something that I'm going to call here morphological disambiguation. This is actually taking the decision how to break down the words into morphemes, and then pretend that Hebrew is like English. That's actually a little bit more reasonable to do, because then the models have the same unit of processing as they assume, but this will be problematic because we are going to experience a lot of errors in the word decomposition. Why? Because for the word decomposition, we basically need information that may be farther in the sentence and comes from the global context, and these errors, we will not be able to recover from them down the pipeline. So again, it works okay for some tasks, but it is not optimal. So what can we do next? We can do something even more sophisticated, which is to jointly solve the problem. So doing the morphological decomposition in the context of the task we're interested in, for instance, semantic parsing or syntactic parsing or information extraction. And this is actually quite sound. I can advance several linguistic arguments why this is sound. But this requires research, because it's not straightforward how to devise a model that applies the local decision and the global decision at the same time. And this is precisely what we do at the research lab. We take tasks, modern Hebrew tasks, and we jointly solve the morphological, the word level complexity, and the more global task, be it semantic parsing, syntactic parsing, named entity recognition, and so on. What I'm going to present today is the essentials of a parser that is called YAP. Do people know YAP in the audience? Did anyone use it, download it? Do people know how it works, how YAP works? So, okay, much less, maybe even no one. So now you will know, or at least you will know the basics, the basic principles that underlie YAP. And with many of these basic principles, we actually develop models for more tasks. So YAP is a model that does morphological disambiguation and syntactic parsing, and it implements this objective function. This is going to be the most technical slide in the presentation. We have an input, which is a sequence of tokens. Tokens are these space-delimited tokens, like Betzilam or B'Tselem, and it's going to be represented by means of a lattice. The lattice structure essentially lists all the possible decompositions. We are doing it in an economic and efficient way. And each arc in this lattice corresponds to one morpheme. So this particular one I highlighted is tsel, and this is a noun. And there is another morpheme, which is a hey yedia, for instance, and a different morpheme, which is a verb, hin'im, right? So once we have all possible different morphological decompositions, we want to assign a tree. Each of these arcs is a node in the tree, and you want to assign it a dependency tree, and the dependency tree is one that assigns bilexical dependencies that tell you essentially who did what to whom, really informally speaking. So what we have here, we have a lattice with different paths, many different ways in which the sentence can be decomposed, and each sentence can have multiple possible trees built on top of it. How many trees? Exponentially many trees. So we have different paths with an exponential number of trees for each of these paths, and we need to search through this huge path of analysis, the one pair, morphological analysis and syntactic parse, that is most probable, that a human would choose as most likely. Of course, we do it subconsciously. We want to implement it. And in order to implement it, I'm going to need 3 algorithms. I'm going to need what we call a generative component. The generative component is like your constructor. It knows how to build these complex structures. And usually it knows how to build it by individual incremental steps, so that breaking down the tasks to more smaller, more manageable units. We have a learning component. It can score the structures, right? We need to sort out which ones are best for us. And we need a decoder. A decoder is something that searches through the whole space for the most probable parse, for the most probable tree. And this is also something we want to do very efficiently. We don't want to wait 20 minutes to get our NLP pipeline result. So very briefly, how this thing is implemented, our generative component is a transition system. The transition system knows how to make building steps. So for instance, the morphological transition system knows how to walk through the lattice. So at each step, I have a decision. Here I can go into one of these 3 directions. Here I can go to these 2 directions. And when I get to the end of the token, this happens to be the end of B'Tselem or Betzilam, I can look at the different analysis and use features to re-rank them in context. And also I have a syntactic transition system. The syntactic transition system is something that has a queue, a stack, and certain operations that I can do. I can shift a word from the queue to the stack. I can connect 2 words in the stack or connect a word with a different word that is on the top of the buffer. And I'm not going to talk in depth about it. This is all in your favorite natural language processing books. This is all very standard. And this is how it's formalized. So once we have a constructor, this thing that knows how to construct paths and how to construct trees, we can search through them, and obviously we are not going to go over the entire space. We are going to use beam search. This means that at any point we are going to apply all possible actions. We are going to score the partial structures that we have, keep the best K, and move on. For these K elements, we're going to do all possible actions, score all the possible actions, structures that we get, and continue with the best K, and on until we get to the end of the sentence. This is the end of our buffer, and then we can score them or rescore them and get the most probable tree. Not really, because this is not how we train it, and this is the question is in place because now I have to tell you how I train it. And the way I train it is using the structured perceptron. This is also very well known. Essentially, it does this like gradient descent thing. We loop through the data. Every time we pass a sentence, we continue to move to construct these trees according to the current weights we have. We rescore the trees, and at the point our goal tree, our ground truth, falls out of the beam, we know that we're going in the wrong direction. We cut the training, we update all weights, and we go back to the beginning. So we loop through all the data, we loop through the different sentences, and once the parse starts to converge on the depth set, we know that we have proper weights to score the beam. So this can, of course, be told in a much longer story, but we don't have that much time here, so feel free to ask me later. So we have a constructor, the transition system. We have a decoding element, and we have a learning component. And by the way, the learning component that I use, I can use a different learning component. Essentially, what I need to have is a scoring function to score trees, and I can train it in whatever way I want. It could be linear or non-linear. In particular, YAP is using a linear function. So now that I have this, I can do several things. I can implement a pipeline where I sort out the morphological structure, take the best one, morphological structure from the beam, and give it to the syntactic component. I can do the morphological thing again, but keep the entire beam and use the syntactic component to re-rank the beam. So these K elements to decide what's most probable in terms of syntax, in terms of global context. Or I can actually make these morphological and syntactic steps interchangeably. So every time I make a morphological decision, I can also make a syntactic decision that sort of matches the current breakdown. And when I train these together, I actually have the chance to influence on parse errors while I'm training it and choose better morphological components up front. Does it work? So from our experience, yes, it works. What does it mean that it works? So we trained it on 5,000 sentences. This is not very much. There is an effort you've heard about to annotate 50K sentences in Hebrew, but now we work with 5K, and we score both the morphological component, this sort of orange one, and the syntactic component. All the code is, by the way, open, and it's on our GitHub. And what we can see is on our development set already, the morphological component scores much better inside the joint model than it scored as a standalone component. And when we move to a test environment, out of domain, if you will, both the morphological and the syntactic components are much, much better. This means that it is much better in recovering from errors. When we test it, comparing to previous benchmarks, so previous benchmarks of about a decade ago are easier because these are benchmarks where linguists did the morphological decomposition. This, of course, cannot scale, but this is a good place to test which parser does a better syntactic analysis. We get substantial improvement relative to the previous state of the art in Hebrew NLP. And we also did a very detailed error analysis by a linguist, actually checking for every type of linguistic error how many errors each of these models makes, and we see that we cut our linguistic errors, so to speak, basically in half. So for errors where the gold standard is wrong, okay, we make mistakes with respect to the gold standard because we cannot recover from it. But for linguistic problems that have to get solved, the joint model actually gets to solve about half of them. Maybe even more, depends on the kind of the error. Okay. So after I talked about these numbers, I'm going to try and do this and hope that the internet will allow us to actually show you what YAP is doing in real life. No, it doesn't. So I guess we're disconnected. We're afraid of Corona. It might. Okay. So we're not going to do that, but I'm going to invite you to get on a computer that is connected to the network and try it out. For instance, you can try Ganan Gidel Dagan Bagan and see that it gets the correct analysis. So normally this would be where I end the presentation, but I have some minutes and I also know what you're going to tell me. So you're going to tell me, wait, so we have all these neural models, and what about BERT? I mean, we have Hebrew BERT. It must do a better job than this linear function in the structured perceptron that seems a little bit cumbersome. We know that in English, this does amazingly well and improves the results in all of the possible models. So what happens with BERT? So I'll save you the question. I'll tell you a little bit more about what happens now in my research lab. So we implement a lot of neural models to solve problems, NLP tasks on Hebrew. In particular, I'm going to show here two models. I'm going to show you LSTM CRF with char-based and word-based fastest representation, and I'm going to do results for BERT fine-tuning. All of these results, I score them for segmentation and part-of-speech tags accuracy. The up accuracy is here on the slide. So I'm going to compare the situation where linguists broke down the words into morphemes. So I have 100% accuracy on the morphological decomposition. I'm going to check what happens if someone else broke down the word into morpheme, for instance, yap, that we know will have some initial error at least, or initial noise in the decomposition. I'm going to test the scenario when I don't require segmentation. I just let BERT or whatever model decide how many tags are there and what tags we need in this particular word, so I don't worry about pre-decomposing the input. And I'm going to do something that is joint, that is a little bit similar to what I've shown you before. So we encode the entire lattice space that we've seen in the beginning, and then we let the model choose. So when we use the LSTM CRF, what we see is that the gold segmentation results are actually quite high. But if you remember, these are linguists doing morphological decomposition. This will not scale. We cannot have a linguist in our business parsing manually each of our words morphologically. And once we move to predicted segmentation, for instance, by YAP, but you feel free to try whatever segmenter, you can use UDPipe or Morph, we get a significant drop. And this is already problematic for applications. So we try to do this raw scenario. We try to let the model decide how many tags there are and not to tell this information in advance. This drops a little bit further. This is a harder task with a greater search space. But if we model the space, the search space with the lattices, like I just showed you, we actually get promising results. So, okay, we think that this way to model the space is going to be useful also for neural models that you are going to maybe try to build or work with, in the future. So we go ahead and we try to do it with BERT. And of course, the BERT results, when we have linguists helping with the morphology, they're quite high as YAP, but this will not scale. We don't have these linguists. If we have YAP segmentation, or if we don't have any segmentation, it actually gives a similar result. It doesn't need the external help. It decides on its own what part of speech tags and how many, but it's not very good. This 92 is quite low for applications. It's kind of an error every 10 words. So we want to do it with joint modeling, right? Maybe we want to take these lattices and we feel that this is going to be promising, but this is actually impossible. And just to get a glimpse to why this is impossible, I'm going to get you back to this figure that we had in the beginning. So what is BERT? BERT is a contextualized word representation. So you get a vector according to the context that you have. But if you're in a lattice, you don't know the context that you have. You just know very many different contexts in which you might be. So BERT cannot assign this ambiguous interpretation. It needs to know a single context. And this is why BERT will not like, so to speak, the kind of joint modeling strategies that I talk about. So this is a huge, huge research question that we are now working to resolve, and we're hoping to have in the future some kind of Hebrew BERT or Aleph BERT, as we call it in our research lab. So to quickly summarize, in the 30 seconds left that I have, there are very many tasks to tackle in Hebrew: sentiment analysis, NER, information extraction, co-reference resolution, and every other task you can think of. But we also need strategies. So we need to think how to retrain and pre-train those neural models and strategies, how to develop joint modeling in the neural paradigm. And what we really need is maybe our own little Sesame Street. So we need question answering benchmarks and natural language inference benchmarks and reading comprehension benchmarks. We want to see that our Hebrew AI can actually answer questions like 10 years old, schooler. And if someone has this kind of annotated data that you want to check our Hebrew AI system, please approach me. We'll be happy to take up the challenge. What can we do? We can work together towards it. We are there to solve these tough challenges. And while Hebrew NLP is extremely challenging, it's also feasible. It's important for me to say that it's feasible once it's done in the proper setup, the proper linguistic setup. We rely heavily on joint modeling of the different layers, and there's a lot more to be done. Please use these models. They're free for you in your own systems, in your business. We don't even have to know who you are. Communicate with us. What are the bottlenecks? We want more research challenges. We will take it up. We will develop these further models. And feel free to further contribute. So thank you very much.